Okay. Yeah. I hope I am audible and visible, no? So my slides are visible. Okay, thank you. Yeah. So yes, as I mentioned that dialogue systems, there are different components of the dialogue system. So I just discussed about one component which is called the dialogue act classification. Now I will discuss about the other components. So one important component is the intent detection and the slot filling. So intent detection basically aims to detect the communicative intention of the speaker, and the slot filling module basically it helps in extracting the the important information from the user's utterance. So this is the problem statement. You can see that we have to intent detection and slot filling are the task of interpreting user comments or queries by extracting the intent and the relevant slots. Intent detection is a classification task which maps an observation sequence to a particular label Y to acquire the most probable intent label given some word sequence. So user is saying something and now we have to map this to an intent. Okay. So what is the communicative intention of the user? That is now we have to understand basically. So, and the slot filling is extracting the useful information from the dialogue. So like if I am saying that I want to book a flight from Patna to Kolkata, then Patna and Kolkata, these are the useful information because these are the source city and the destination city. Because in a task oriented setup where the actual conversational agent or the virtual agent is trying to solve a particular task, from the user's utterance, we need to extract the useful information. And then by using those useful information, we have to basically search the database. And then we have to extract the relevant information. So intent detection is framed as a classification task, which intent detection is a classification task, but slot detection is basically, to identify the relevant information from the user's utterance. So it basically maps an observation sequence to a sequence of labels to acquire the most probable slot sequence given some word sequence. For example, suppose the sentence that the user's utterance is first class fares from Boston to Denver, then the intent is the airfare because the user is asking about the airfare, and the slots are this first is the B class type, class is the I class type, Boston is the B from location, Denver is the B2 location. So these are the different slots, and the actual intent is basically the airfare. So here, as I mentioned, that we are using the data sets ATIS. It contains user utterances related to the air travel information system. Then we also have the SNPs dataset, which contains several day-to-day user comment categories like playing a song, booking a restaurant, etc. And we also have the MIT restaurant movie corpus, which contains user utterances related to movie and the restaurant domain. So these are the three datasets that we have used. ATIS, which is the air travel information system, which is a task-oriented setting. I already discussed about this dataset. Now there is another dataset called the SNPs, which contains several day-to-day user comment categories like playing a song, booking a restaurant, etc. And third is the MIT restaurant movie corpus, which contains some user utterances related to the movie and the restaurant domain. So let me just discuss about some approaches which are very much popularly used for solving the intent and the slot detection. So one could be the LSTM and GRU followed by CRF. So you know that this slot is a sequence labeling task, because if the previous one was the brief from location, then maybe next would be the I from location. So basically, it's a sequence labeling task. That's why in the last layer, we are using the CRF. So this particular approach combines a LSTM GRU network with the CRF network to obtain a LSTM GRU CRF model. The idea behind such an approach is that the network can then efficiently utilize the past input features because of the presence of the LSTM layer, followed by CRF layer, which can then add sentence level tag information. So basically here you can see that we are not only using we are using the context. because based on the context only we have to identify the intent of the slots. So the idea behind such an approach is that this network can then efficiently utilize the past input features because of the presence of the LSTM layer followed by a CRF layer, which can then add sentence level tag information. So basically, you know, we want to identify the context, and you know, LSTM or the by LSTM are very good in capturing the context, and that's why LSTM is basically using. CRF layer predicts the current tag with the help of the past and the future tags, which is quite similar to a bidirectional LSTM or GRU network that makes use of past and future input features. So CRF layer predicts the current tag with the help of the past and the future tags. Then there is a second model which is using the BiLSTM GRU CRF network. So BiLSTM GRU, because now it can also see the context. It's a window, left and the right portion can be easily checked. And then finally the CRF is there for the prediction. So this model combines a bidirectional LSTM or GRU network with a CRU model to obtain a BiLSTM GRU CRU model. Along with the past input features and the sentence level tag information as used in a LSTM GRU CRF model, the model utilizes the future input features as well. So this is the model. So you can see that either we can have a GRU LSTM, show flights from Tacoma to Nash Valley. So these are the words given to the individually to the GRU LSTM model. And then we are predicting B from location city name, B to location city name. Now it is a BiLSTM GRU CRU network. So you can see here we are seeing the forward context as well as the backward context. There is a forward label, forward layer LSTMs, and there is a forward layer LSTMs, and the same sentence. So that way we can easily capture the context, left and right context. Yeah, Joby, I think we can also use these are, we are just discussing, or use one deep LSTM network instead of adding CS. Okay, you want to mention that finally why CRF. Yeah, that is also a good approach that can also be done. But yeah, we just want to combine, we want to make a hybrid approach. We want to use LSTM and CRF together, both together. Okay, so that's why we are extracting the feature vectors from the LSTM and then we are passing through CRF. But yes, here you can easily see that, CRF can also be replaced by LSTM. Yes, so this is the BiLSTM CRF network, and these are the results. We did we applied various models: LSTM, GRU, BiLSTM, BiGRU, CRF only, then LSTM and CRF combined, GRU CRF combined, BiLSTM CRF combined, BiGRU CRF combined. So you can see when we are making a hybrid model, like we are combining CRF with the BiLSTM or CRF with the BiGRU. So we are getting the CRF with the BiLSTM is giving you the best accuracy and the best F1 score. So now, these are all about the intent and the slot. So you can see that intent detection is a kind of a classification framework only. It's again very similar to dialogue classification. In the sentence level or in the utterance level, we need to find out the intent. And slots are basically discerning about the important information, extracting the important information from the user's utterance. So yeah, so these are the intent and the slot detection. Now I will discuss about the other component, which is called the dialogue manager. Okay, so dialogue management, the dialogue manager. So dialogue manager is a reinforcement learning based agent. So basically here it's a we need to map the state into action. So the main function of the dialogue management component is to control the flow of the dialogue, and this involves the following task. So basically, in a task-oriented setting, somehow we have to keep a count or keep a track of whether we have sufficient information from the user side to search in the database. Because suppose the user wants to wants for a flight. Hello, yes, any question? So suppose the user wants to book a flight ticket. So then first task of the conversational agent is to gather all the relevant information from the user, like the source city, destination city, class, date, time. All those information have to be collected from the user's utterance. So the main function of the dialogue management component is to control the flow of the dialogue, and this involves the following task: determining whether sufficient information has been elicited from the user in order to take a suitable action. Hello? Can you please mute Tulsa? Yeah. Yeah. Okay, so I hope I am audible. So basically, you know, the main function of the dialogue manager is to control the flow of the dialogue. And this involves identifying the relevant information from the user. So if suppose you want to solve a particular task, we need to extract relevant information from the user. For example, as I have given the example, like user wants to book a flight ticket from a source city to a destination city. So there are many relevant information like the city name, the source city name, the destination city name, date, time, whether the user wants to go by business class or the economy class. So all these information we need to collect from the user, and then after once the all information are collected, the database search can be made, and then accordingly accordingly the result can be shown to the user. So this is the overall task of the dialogue manager. So dialogue manager is basically keeping a track whether we have sufficient information from the user or we need to ask some additional information to the user. So here executing an action means communicating with an application and communicating with the user. So this is the reinforcement learning is a paradigm of machine learning. In machine learning, there are three important paradigms: supervised learning, unsupervised learning, and the reinforcement learning. So here in the reinforcement learning, suppose agent wants to solve a particular task, and agent is getting some signal from the environment. Okay, so agent has taken some action. So we don't know the actual class level of the action, but we can give some signal to the agent so that the agent can easily understand whether the action is correct or wrong. So reinforcement learning allows the machine or software agent to learn its ideal behavior based on feedback from the environment, that is the rewards. So here you can see a picture that there is an agent or chatbot, and now this chatbot is taking an action, and now this action is given to the environment, and the environment. One second. Yeah. Hello. Yeah, sorry. So yes, so basically, this is the reinforcement learning. So you can see that in the reinforcement learning there is an agent and there is an environment. So the agent is basically taking an action, and then this action is evaluated by the environment. So this action, for a particular action, we have a reward or a penalty, and then initially there is a state ST, and after taking the action AT, the agent will go to a new state ST plus 1. So basically there is a state ST, and the agent is this state ST is given to the agent. Agent is taking an action AT, and then the environment is basically evaluating the action, and then basically the environment is generating the new reward RT plus 1, and it is also going to the new state ST plus 1. So this is the overall reinforcement learning process. So the underlying principle behind reinforcement learning is the law of effect. You do something, something good happens. So you try to do it more often if a similar situation arises. You do something, something bad happens. So you try to do it less often if a similar situation arises. So basically here, we don't have the actual supervised signal, but the action is evaluated in terms of the reward and the penalty. So if the action is suitable, then there will be a reward. Otherwise, there will be a penalty to the agent. So this is basically the reinforcement learning. So here, why reinforcement learning? Because we don't have much label data. So, but given a state, we need to find out the action. So basically, reinforcement learning is the most suitable one, and that's why basically reinforcement learning is used for in dialog manager, because in dialog manager we have a state. State is nothing but all the slot value pairs. So we are extracting the relevant information from the user's utterance, and those are basically the state. And now given the state, we are finding out the action. So, and that can be easily done by the reinforcement learning. So in reinforcement learning based chatbot, these are the steps. So that the RL chatbot takes an action AT at time T, which is converted into speech to text speech by text to speech unit. Okay, so so first, suppose the RL is taking an action AT. For example, this is the RL chatbot which is taking an action AT. So this action is translated into speech signal by text to speech module. So there is a text to speech module, and which is translating the action into the speech signal. So, and this speech signal is given to the user. Now this user is basically there is a user is uttering something. So there is a utterance by the user, and there is a speech to text module. So this speech to text module basically translates it basically generates the utterance from the speech signal. So there is a speech to text translation module. This basically translates the speech signal into the text signal. So yeah, this is the overall chatbot design. So now suppose there is a action. So this action can be evaluated by the user. Okay, so this action can be evaluated by the environment. So for a given action, the chatbot can be easily given by a reward or a penalty. So this is the overall RL chatbot. So the RL chatbot takes an action AT at time T, which is converted into speech by text to speech unit. The user's response in the form of speech is converted to text by speech to text unit. The output of the speech to text unit, that is the observation, is received by the chatbot. The user may either generate a reward signal explicitly, or it is derived from the user's response. The task of the RL chatbot is to respond in a way so as to maximize the reward. So basically our target is to maximize the reward. So this reward can be either given by the environment, or the reward can be basically given from the generated from the user's utterance. So that is the overall, this is the overall RL chatbot. And in a reinforcement learning, there is basically it is following the Markov decision process. So here there are some, sorry, let me just. Yeah, so in reinforcement learning, this is basically, you can see that it is a Markov decision process. The Markov decision process is described by using these tuples. There is a S is the finite state space. A is the set of actions. R is the reward function. So R is basically function from S to A. Given the state, we have to pick and given a state and the action, there is a reward. So basically it is a function of S into A to a real number. And P is basically the transition model, how the one state is transiting to the other state. So state to state transition is basically controlled by P, and rho is the initial state distribution. So S is the finite state space, A is the finite action space, R is the reward model, P is the transition model, and rho is the initial state distribution. So the idea is to implement reinforcement learning for learning dialogue strategies using the Q learning algorithm. So the Q function is basically a quality function. So basically the Q function measures the quality of a particular state action pair. So given a particular state and taken a particular action, what is the quality of that action given the particular state? So the quality of the action is basically determined by this Q function. So our main task is to basically maximize the Q function, and this Q function can be estimated by the Bellman equation. And basically there could be a neural network which can somehow approximate the Q value function. So hence the Q function will be approximated using a neural network, which is called the deep RL. So this is the overall the Markov decision process. We have a set of states, we have a set of actions. R is a reward form model, P is the transition model, and rho is the initial state distribution. And basically there is a Q function. So this Q function is a function of S into A, and it basically measures the quality of a particular state given a particular action. So Q learning defines a function QSA, which represents the discounted future reward. So here QSA, this does not only represent the immediate reward, but it is a cumulative reward. Okay, we have to see all the cumulative reward, the immediate reward plus some discounted future reward. So it is a combination of the immediate reward plus a discounted future reward. So Q learning defines a function QSA, which represents the discounted future reward when we perform action A in state S and continue optimally from that point on. So basically given a particular state S, we are taking an action A, and then Q basically indicates the cumulative reward. So the way to think about QSA is that it is the best possible score at the end of an episode after performing action A in state S. So basically it is an evaluation measure, very much similar to our accuracy or the F measure. So this Q value or the Q function is a kind of a evaluation measure of how good the action A is given the state S. So it is called Q function because it represents the quality of certain action in given state. If you want to select the action that results in the highest score at the end of an episode, then we have to pick the action with the highest Q value. So basically S is the current state, A is the current action. We have to pick that particular action A which maximizes the Q value. Okay, so that is the basically the pi S. Okay, so basically that given a particular state S and given a particular action A, we have to pick that particular action A which maximizes this Q value. The main idea in Q learning is that we can iteratively approximate the Q function using the Bellman equation. So QSA equal to R is the immediate reward, plus gamma is the discount factor. Now we have to find out the particular action A dash, whose value is the maximum. So we have to find out, it is as I mentioned that it is a immediate reward plus discounted future rewards. So gamma is basically discount factor. So gamma determines the weightage of the future rewards. So that if suppose the current state is S and the current action is A, the immediate reward is R. And now after taking the action A, this MDP will move to the state S dash. And from the S dash, now we again have to find out the optimal action which will maximize the Q value. Okay, so this portion Q S dash A dash max over A dash, this will give us the maximal action A dash, corresponding to which we have the maximum Q value. So this is the future reward. So gamma is the discount factor between 0 and 1. And this is the QSA is basically immediate reward plus the discount factor into the future reward. So basically we have to take the particular action A which maximizes this Q value. So now this deep Q network in DRL, the Q function is implemented and approximated using a neural network. That is, by acting as a function approximator, we can take any number of possible states that can be represented as a vector and learn to map them to Q values. Okay, so basically this Q value can be approximated by a neural network. You know, neural network is a function approximator. So the neural network can be trained to approximate the Q value. So the Q function of a DQN agent is parameterized as Q. S is the set of S is the current state, A is the action, theta I, where theta i's are the parameters or the weights of the neural network at iteration I. So a Q network can be trained by minimizing a sequence of loss functions L theta I that get updated at each iteration I as follows. So you can see that MB is the mini batch. We are considering a batch, and then we are computing basically we are getting the what is the actual value and what is the value determined from the neural network. So theta i's are the parameters of the neural network at iteration I. Theta I dash are the target parameters of the neural network at iteration I. So these are the target parameters. So we are computing this Q function, what is the target value and what is the actual value. And accordingly, we are calculating a loss function, and this loss is used to train the deep Q network. So what the current deep neural network is giving and what is the actual value of the Q function. So that difference is calculated, and that is the loss function. And by using the loss function, we are basically updating the deep neural network. So and now there is a algorithm called the double deep Q network. So here you can see that the same network is basically here. For example, we are using the almost the same network to find out this Q value. So one issue with the DQN algorithm is that it is more likely to overestimate the Q function values due to the Maxine equation used to set targets. So here, instead of using only a single network, there are two networks very similar into each other, and then this is called a double deep Q network. The DDQN algorithm is said to overcome this particular problem. In this algorithm, two Q functions, Q1 and Q2, are independently learned. One function is then used to determine the maximizing action, and second is used to estimate the value. Okay, so there are two functions, Q1 and Q2. And accordingly, you can see the DDQN algorithm is developed. Hence, it was proven that by decoupling the maximizing action from its value in this way, one can indeed eliminate the maximization bias. Now, there is also another algorithm which is called the priority experience replay. So, in this priority experience replay, that we are not considering all the samples. So here you have seen that there is a mini batch. So a set of utterances are used for training the network. So in priority experiments replay, so another concept that is acknowledged in the literature is how the experiences are used for training. When all the samples are treated alike, one of the aspects which gets ignored is that learning happens more from some transitions than from others. Okay, so basically, some samples are more important than others. So basically, that here in case of priority experience replay, some samples are given more weightage than the others. So PAR is one such strategy that tries to leverage this fact by changing the sampling distribution. So this in priority experience replay, we are putting more importance to some of the samples than others. So PAR is one such strategy that tries to leverage this fact by changing the sampling distribution. The main idea is that those transitions are preferred that do not fit well to the current estimate of the Q function, because these are some transitions from which maximum learning can happen. So basically, this is the thing that some samples are given more importance, or some samples are used more compared to the others. So we are changing the distribution. So we are randomly selecting some samples, but we are changing the distribution depending on the errors. The main idea is that those transitions are preferred that do not fit well to the current estimate of the Q function, because these are some transitions from which maximum learning can happen. So basically, now I will discuss about one such dialogue management algorithm. So how reinforcement learning can be used to develop a dialogue manager. So you know that here we will discuss about the hierarchical reinforcement learning, because sometimes it may happen that a particular utterance may contain multiple intents. Okay, so if suppose the user's utterance is having multiple intents, and you know, in order to serve a particular intent, we need one deep queue network. So you know, because one deep queue network is used to take the appropriate action for a particular intent, because its task is to solve the particular intent or to gather sufficient information to solve the particular intent. And for that, for a particular deep queue network is there to to basically take appropriate action for a particular intent. So if we have multiple intents, then there will be multiple networks. So we need to transit from one network to another, you know, by using by using this hierarchical reinforcement learning concept. So we would like to develop a hierarchical dialogue management strategy for task-oriented virtual agent. So basically, now I will discuss about this. So this is useful for managing the multi-intent conversations. So suppose in some conversations there are multiple intents. So and and for each intent there is a deep queue network. So we are using the reinforcement learning for solving these multi-intent conversations. So what is multi-intent? Intent captures the main communicative intention of the user's utterances. Multi-intent captures more than one intentions present in the user utterance. So show me flights and cheapest fares from Pittsburgh to Denver. So here there are multiple intents like flight and the airfare. So show me flights and cheapest fares. So you know, it is showing about it is asking to show the flights and also the cheapest fares from Pittsburgh to Denver. So there are two intents, flight and the airfare. So both the intents are served in a single, you know, we have to develop a deep hierarchical RL framework which can try to solve both the intents. So this is our proposed methodology. So basically there is an intent state space. So intent state space will, you know, try to identify which intents are present. So it's a binary vector. So the length of this vector is equal to the number of intents present in the data set. So if a particular utterance is having two intents active, then the corresponding values will be equal to 1. So this is a multi-hot encoded intent state space. So now basically accordingly we have to basically select a particular for a particular, as I mentioned that for each intent there is a separate network. For example, this network is responsible for serving intent 1. This network is responsible for serving intent 2. This is for intent n. And there is a global slot tracker. So these are the slot values. So some slot values are shared between the intents. For example, show me the flights and the cheapest fare. So you know that here some slots are very common, like the source city, destination city, and then the date, time. So all these information are very common between these intents. So that's why there is a global slot tracker. So suppose while we are serving the first intent, like the show me flights. So that time, suppose already the agent has gathered information about the source city, destination city, date, and time. So those information are kept in the global slot tracker, so that when it will serve the next intent, which is the airfare, it should not ask again about those slots. Okay, so it will get the values of the slots from this global slot tracker only. So basically, this is the advantage of having a global slot tracker. So global slot tracker tracks all the slot values. So basically, and for each intent there is a individual module or individual deep queue network, and there is a switching from one module to another intent module, because as I mentioned, some utterances are having multiple intents. So we need to serve all the intents together, all the intents one by one. So initially one intent, one network is invoked, and then corresponding slots will be extracted, and then it will jump to the next network for serving the next intent. And this way, and finally, when all the intents in a particular utterance will be served, you know, basically you can see that response will be generated. So it will basically interact with the natural language generation module to generate the responses. So this is the basically proposed approach, that there is a hierarchical model. So there is a in the top level there is a higher level hierarchy. So this higher level policy will decide which intent to serve first. As there are multiple intents, so there is a higher level policy which will decide which intent to serve first, and then there is a lower level intent policies. So for each intent there is an individual policy. So train is set up networks where each network represents servicing a particular intent to complete a particular sub-dialogue. Each DRL network exhibits unique behavior while interacting with the user to complete the task optimally. Therefore, in a network of deep reinforcement agents, an action selection is performed based on an optimal policy. Yes, yeah, please.
Ma'am, what do you mean when you say a slot tracker in the previous slide? I don't understand that part actually.
So as I mentioned, no, so like if suppose you are saying show me flights. So here, in order to, this is an intent. So intent is user is interested in seeing the flight information. Okay. So in order to serve this particular intent, you need some further information. No. So basically the agent will keep on conversing with the user to gather more information, because in order to search in the database, you need some further information like what is the source city, destination city, date, time, all this information you basically need. So those are basically called the slots. So source city is one slot, destination city is another slot, date in another slot, time is another slot. Then whether the user is interested to fly in business class or the economy class, that is another slot. Or if the user is having any preference on the airlines, so that is another slot. So these are the slots or the relevant information which are required to serve the user's task. So user is interested in booking a flight, but before the booking the flight, the conversational agent has to ask some other questions also. So it is not a single utterance task, only by knowing that user is interested in booking a flight, the agent will not be able to make the reservation. So the agent requires some further information. So this further information are knowing about the source city, destination city, date, time, airlines, preferred airlines, or the business or the economic class. So these are basically the slots. And as I mentioned that as there are multiple intents, there are some common slots like this flight and the cheapest fare. Both these intents have the common slots like source city, destination city, date, and the time. So that's why we are using a global slot tracker, which is a global array of available slots. So while we are servicing a particular intent, already maybe user have already specified some slots. So those slot values are already available in this array. Okay. So when it is servicing the next intent, it will not ask the same question. It will not repeat the same question to the user, because then user will not be happy with the situation. So that's why if there are some common slots, we are keeping the values of those common slots in the global slot tracker, so that all the intents can basically use the common slot information. Is it okay?
Yes, ma'am.
Yeah. So, yes, so this is the, so basically as I was discussing that for each intent, there is a deep queue network, okay? Because, a deep queue network is, in the input, we have the states, and the output, we have the action. It is basically determining the optimal policy to map state into action. So so basically for each intent there is a deep queue network. Therefore, in a network of deep reinforcement agents, an action selection is performed based on an optimal policy, which is this one. So it is basically Q star. So Q star is the deep queue network. So it is basically given a state S. It is selecting the optimal action A. Theta are the parameters. So is used for low level hierarchy within a DRL method model transition, where intent is set up intents is determined as this. So basically there are two hierarchies. At first there is a higher level policy. So there's a higher level policy selecting the appropriate intent which will be served next. and accordingly the corresponding deep queue network will be invoked, and then accordingly the lower level intent policy will be invoked, and it will be executed, and it will try to collect all the relevant slot information from the user. So that is the thing that here you can see that this is a Markov decision process, as I mentioned earlier. So it finds its applicability in any domain having n number of intents and n number of slots. So this is a very generic framework. It can be applied to any domain where we have to solve multiple intents simultaneously and having m number of slots. So at a given time, the state space is having two components, S1 and S2. S1, it is a state which is a tuple of n variables corresponding to the number of intents in a particular domain. It keeps track of the current intent output from the IC module being serviced by the VA in the form of one-hot encoded vector. So basically, you know, the S1 is it keeps track of the current intent output from the IC module being serviced by the VA in the form of one hot encoded vector. This in turn invokes the appropriate RL model corresponding to the intent being served. State S1 represents the top level hierarchy of the dialog manager. So basically, you can see that S1 represents the intents which are present in a particular utterance. So it is basically one, you know, it's a binary representation. So yeah, the length of S1 is equal to number of possible intents, and at a time, multiple intents can be present in a particular dialog. And for each of the intents, S2 is a tuple of variables of the length equal to the number of slots required to be filled up for the particular intent. So for a particular intent, in order to serve a particular intent, you need to have some minimum number of slots because we need to search in the database. And for efficient database search, we need to have some slots available for servicing a particular intent. So S2 denotes all those set of slots which are required to serve a particular intent. So this state represents the bottom-up hierarchy of the dialog manager. So these slot variables in turn correspond to confidence scores of different slots, which are the probability values outputted from the slot module, representing the confidence of the modules in predicting different slot levels. So this S2 is basically a real vector. So the length of S2 is equal to the number of slots required to serve a particular intent, and the value represents the confidence value. So user is saying something, there is a user's utterance. From the user's utterance, we are extracting the slots. So there is a classifier which is extracting the slots with some confidence values. And those confidence values are basically put in S2. Now there is an action space. The action space constitutes of 21 unique actions categorized in 3 different classes: ask, re-ask or confirmation, and salutation. So such as ask class, re-ask, GCT, etc. So basically there are 21 such unique categories. So given a state, it will pick a particular action. So now, as I mentioned, that in reinforcement learning, reward functions play the major role, because here in unlike supervised learning, we don't know the actual class level. Like given a particular state, which is the optimal action, that we don't know. So this deep queue network is predicting an action depending on the policy that it has learned, and now whether this action is correct or not, that is checked by the reward function. Okay, there is a signal. So whether this action is correct or not. So different reward function at different time steps for different action in conversation. So for any action except terminating action, we have this R, S, A, S dash. S is the current state, S dash is the next state, and A is the current action. So you have this NS. State is the summation of the confidence scores of all state variables in the state vector S obtained after taking an action A in state S. Okay, so we have this we have the S2. We have the S2. So suppose after taking an action, so action is translated into a response. Now user has uttered something, and now there are more slots present in the user's utterance. So NS is the confidence score of those slot values, and CS was the original confidence scores. So this difference. So whether we are getting more slot information after taking an action A or not, that is basically checked by this particular reward. So suppose after taking the action A in state S, we are getting some more, we are getting some more slot values, and there are some corresponding confidence scores as well. So this is the difference. Okay. So NA state is the summation of the confidence scores of all state variables in the state vector S obtained after taking action A in state S. CS is the summation of confidence scores of all state variables in state vector S. So, and W1 is used to encourage the agent to act in a way so as to increase the confidence of the acquired slot. So these W1 and W2 are the parameters. So W2 is, is used to discourage unnecessary questions, iterations with the user. So this is a penalty basically, and W1 is basically a kind of multiplication factor. So here, after some ablation studies, we have selected the value of 1 for W2 and 8 for W1. So this reward function basically helps us in getting more slot information in the state tracker. So we have the state S2. So in S2, there must be more number of slots available. So this reward basically helps in taking those actions which are basically improving the confidence scores of the slots present in S2. Now for the terminating action, the condition is that how many slots has a confidence score above a threshold, say 0.7. The condition is satisfied when all slots match the criteria. Okay, so for example, if the condition, so if suppose at the terminating condition, you have the S2, in S2, you have all the slots and the corresponding confidence scores. If for all the slots, the confidence score is greater than 0.7, then that means it is a good terminating condition. So basically, if it is satisfied, then basically we are giving this reward W1 into summation over the CS. But suppose when we are terminating, all the confidence values of all the slots are not 0.7. In that case, there is a the reward is like this: EV minus CS. It is basically a penalty, because though we are selecting the terminating action, but basically we have not reached the terminating state because the confidence scores of all the slots are not 0.7. So it is not a terminating state, but still we have selected the terminating action. So this is the reward function model. So you can see that for different Markov decision process, how the rewards are varying. So you can see that these are the iterations versus the rewards for different MDP. So that when we are considering the flat RL, like there are no hierarchies. Like here we are using the two hierarchies, no, the hierarchy, top level and the bottom level. So the top level is selecting the appropriate intent, and then there is a lower level hierarchy servicing the individual intents. So so if you are using all the intents at together, then basically this is called the flat RL, and this is the learning curves. So then it is very difficult for the agent to learn anything. But otherwise, you can see that with the iterations, the average reward is improving, and finally there is a saturation. So this is an example of the developed virtual agent that we have developed. Suppose initially there is no intent, so you can see the S1 is 0000. There are actually 5 intents, and none of the intent is present, so that's why all the values are 0. Now the agent is saying, hello, how can I help you? User is saying, I would like to travel from Pittsburgh to Denver. Okay, so system log is intent changed to flight, because the user is saying, I would like to travel from Pittsburgh to Denver. So the intent changed to flight. So you can see that the corresponding one is in the flight. This is the value corresponding to flight intent. So we're getting a value of 1 here. Now the S2 is all the confidence values of the slots. So here you can see in this utterance, there are 2 slots present, Pittsburgh and Denver. This is the source city and this is the destination city. So the corresponding confidence score of the classifiers are 0.9 and 0.97. So we are putting these confidence values in the S2. Now the agent is asking, please specify the class of flight. So because given this state, now the next to serve the particular intent, which is the flight intent, the agent needs to know the class of the flight, whether the user is interested in economy class or in the business class. So the user is saying, I want to travel in economy class. So, this is a kind of a slot only. This economy is now a slot. The corresponding confidence is 0.94. So, we have put the value 0.94 here. Now the agent is asking about the date and the time, because without the date and the time, the database search is not possible. So the agent is asking specify the time and date. So the user is saying on 4th January at morning. So this 4th January in the morning, this is the date and the time. So the corresponding slot values are this. Now the agent is closing the conversation. The flights from Pittsburgh to Denver on 4th January at morning by economy class are this. So now after as all the slot values are now present, so now it will search in the database and basically it will get some flight information, and that flight information is displayed to the agent. So do you need anything else? So basically you can see that user is saying show me the cheapest fares. So basically the user is saying show me the cheapest fare. So the intent has now changed to airfare. So now you can see initially the intent was flight, but now intent is changed to airfare. So that now in the hierarchy in the top level, this value is equal to 1. And basically it's you can see that it is using it is a global slot tracker. So this S2 is basically common across all the intents. So it is borrowing the confidence values from the previous S2, okay? Because there are many common intents, common slots, like the source city, destination city, date and time. These are the common slots. So basically it is borrowing the confidence values of the slots from the previous intent. Then agent is asking round trip or one-way fare. This is a new slot because this slot was not available in case of flight intent, but this slot is required for the price intent. So it is asking round trip or the one-way fare. So accordingly, the user is answering round trip. The corresponding slot is detected and the corresponding confidence is value is entered into S2. So now all the slots have received the confidence values, now we can easily search in the database, and then the database result is displayed by the agent. The cheapest fare of the flight from Pittsburgh to Denver on 4th January and round trip via economy class is $1,000 for this particular flight. So then again, agent is asking, do you need anything else? User is saying, no, thanks. So the system basically now there is no intent, so no servicing is required. So you can easily see that now here there is a hierarchical reinforcement learning. In the top level, we have the intent, we have to invoke there is an intent detection module. So basically it is identifying the intent and then it is invoking the corresponding deep queue network. And in the second level, it is extracting all the slot confidence values of all the slots. So now we intend to exploit the fact that even though there is a language difference, but the semantic relation of a specific task coexisting irrespective of any language barrier. So this initially we developed the model is in English, but how can we also develop the same virtual agent in Hindi? So that in case of dialog manager, no change is required because a dialog manager deals with the state and the action. So state is nothing but the slot values and their confidence values. And the action is basically, whether ask, reask, or some other actions. There are 20 such actions. So it is a semantic space. So here language doesn't matter. So basically the dialog manager remains same. If you are using, if you are developing the a virtual assistant in Hindi, basically we'll be using the same dialog manager. So we intend to exploit the fact that even though there is a language difference, but the semantic relation of a specific task coexist irrespective of any language barriers. Thus, we have reused the same DM module trained once, and by replacing its supporting modules such as natural language understanding and natural language generation by the corresponding Hindi counterpart. So yes, indeed, now we need to make some changes in the natural language understanding module because the intent detection and the slot identification, those modules now they have to deal with the Hindi language utterance. So basically, we need to change some. We need to use some different word embedding techniques to generate the vector representations for the Hindi words. Because till now we have used the globe or the what to vec, which are generating the vector representations for the English words. But if we are, if the speaker is speaking in Hindi language, then we need to use some other embedding techniques to generate the vector representations of the Hindi words. So basically, we have to use the some other the natural language understanding module, which can easily understand the Hindi language, and also the natural language generation module, because now the the agent's response will be also in Hindi. So we need to develop the natural language generation in Hindi. So the IC and the ACM module have been trained on the semantic tagging corpus developed in Hindi for the 80s dataset. So what we have done is that we have translated the 80s dataset into Hindi. So initially 80s was in English, but now we have translated the 80s into Hindi, and then this Hindi translated 80s dataset used to develop the intent module and the slot module. So following the similar approach, the DMM module can be reused for any other language for the related task, given that there is an availability of a semantic tagging corpus for the task in that given language. So here you can easily see some examples. So उड़ान जात पाठशाली पे आपका स्वागत है. जमीनी परिवहन की क्या सुविधा है? So system log change, intent change to ground service, and the corresponding slot is 00. Agent is asking कृपया जमीनी सेवा के स्थान और परिवहन प्रकार के निर्दिष्ट करें. So user is saying डेनवर में जिसमें लिमोसिन सेवा है. So now you can easily see it is extracting all the slot values, Denover and the limousine, and the corresponding confidence scores are stored in S2. यहाँ लिमोसिन सेवा डेमोना में भी उपलब्ध है. क्या आप कुछ और जानना चाहते हैं? So user is saying हाँ मुझे उड़ाने दिखाइए. So intent is now changed to flight. Initially it was the ground service. Now the intent is changed to flight. But the slot values are remain 000 because the ground service and the flight, they do not share any common intent. So we are not borrowing any intent from the ground service. जैसे आप कहाँ से कहाँ तक की उड़ान भरना चाहते हैं? So user is saying मैं बोस्टन से डेनवर तक उड़ान भरना चाहता हूँ. So now this Boston and the Denver are the source city and the destination city. So the corresponding slots are identified and the corresponding confidence scores are also identified. So we are keeping this confidence score in the state tracker. So S2 is a state tracker. Now agent is asking कृपया अपनी उड़ान की श्रेणी स्पष्ट करें. So user is saying मैं व्यावसायिक श्रेणी में उड़ान भरना चाहता हूँ. So you know that here the व्यावसायिक श्रेणी or the business class is basically the corresponding slot. So we are extracting the confidence score of the slot, and that is basically added here. Now agent is asking कृपया तारीख और समय स्पष्ट करें. So user मैं 4 जनवरी को सुबह में उड़ान भरना चाहता हूँ. So कृपया तारीख and date and time, the agent is asking about the date and time. So date is 4 जनवरी को सुबह में. So the date and time are mentioned. So the confidence values are extracted and those are added in the state. आपकी Boston say, so now all the values are present, all the slot values are present. So the agent can easily search in the database and the corresponding result can be displayed to the user. आपकी Boston से डेनवर के लिए 4 जनवरी को सुबह की व्यावसायिक श्रेणी की उड़ान है ABC. So it can give some more options. क्या आप कुछ और जानना चाहते हैं? So नहीं धन्यवाद. So basically now there is no intent, so it can terminate this conversation. So this is the virtual agent in Hindi. So basically we do not need to have a separate dialog manager. The dialog manager remains the same. We only need to develop some other intent and the slot modules which can easily extract information from the Hindi text. So now I will now discuss about a particular work where we are dealing with the multimodal information. So as I already mentioned, show you how multimodal information can help in improving the dialogue act classification. Similarly, multimodal information can help, like if we can allow user to while user is basically conversing with the agent, if the user can also express himself or herself through text and the images, like user can also display some images to express himself or herself, and the agent can extract relevant information from the images also, then we can improve the user satisfaction. Because sometimes, as I mentioned, that some concepts are difficult to be expressed using text. So in those cases, user can simply show some images, and it is a task of the virtual agent to identify or to extract relevant information from the images. So this is a multimodal setting. So here the users can express himself or herself through text and the images, and the agent will try to extract the relevant information from the text and the images. So here we are learning a dialogue policy for multi-intent conversations using the hierarchical reinforcement learning. So here there are two levels of hierarchies. So again, there could be multiple intents. So in the top level, we have the intent policy, and in the dual level, we have the for individual intent, we have a individual policy. And now virtual agent is capable of handling the multimodal information. So user can provide information in terms of text or the images, and the virtual agent is capable of extracting relevant information from the images. So user behavior, apart from semantics such as sentiment, basically we are also trying to understand the user sentiment. So suppose when user is conversing, the user is happy. That means the agent's selected action is appropriate. So a sentiment basically gives us an information or indication whether the selected action is correct or not. Suppose agent has selected an action and that action is correct, then the user sentiment would be positive. But suppose the agent has selected an action and the action is not correct, and then the user sentiment would be negative. So basically the user sentiment can provide us a better information about the user satisfaction, and that can provide us a signal incorrectly in basically it can be also used the reward function. So if the sentiment is positive, then the agent can get more reward, and if by taking an action, if the user sentiment becomes negative, then there will be a penalty to the system. So here in this particular work, we have not only have the task oriented reward, which I have already discussed earlier, but here also we have introduced the sentiment based reward. So the idea is to make the users happy, because whenever we are developing some AI assistant, we should also make the users happy or the satisfied. So the user satisfactions or the user's happiness can be easily measured by using the sentiment information. So so basically here we first there are some novelty. So one is that we have developed our own data set. In this particular data set, user is conversing with the virtual agent, not only using the text, but also using the images. So if suppose the user is not able to explain some concept by using text, user is also allowed to show some images, and then the virtual agent can extract relevant information from the images. So, and also there is another important thing that, as I mentioned, that users' utterance can have multiple intents. So in some cases, the needs and queries of the user are complex and the composite. So we can extract multiple intents from the user's utterance. So eventual evaluators and the consumers of any dialogue system are users. The extra feedback from the user in terms of sentiment will steer the VA to be user adapted to learn an efficient dialogue policy. So basically, that here we have introduced two types of rewards: task-oriented reward, which I have already discussed earlier. But apart from task-oriented reward, here there is also a sentiment-based reward. So agent has taken an action, and by using this, after taking this action, if the user's sentiment becomes negative, then there is a penalty. But after taking that action, if the user's sentiment becomes positive, then there is a reward. So in real life conversations, users communicate their choices or queries using text, images, verbal communications. In task-oriented conversations, users take help of images to convey their preferences. So here, basically, we have proposed a novel dialogue policy learning framework to curate a virtual agent that integrates hierarchical value function with deep reinforcement learning to learn strategies for managing multi-intent task-oriented conversations. So here the VA is curated in a manner such that it is capable of handling multimodal information in the form of text and images, communicated by the user in its learning framework. So along with it, sentiment of the user is incorporated to these hierarchical value functions to make the user adaptive to the sentiment of the user. So we basically developed a data set which is called the vCenti VA. So this vCenti VA, here the user is conversing with the agent not only through text but also through the images. And each of these utterances is annotated with the corresponding intent label and also with the slot levels and also with the sentiment levels. So we are considering, in order to develop this vCenti VA data set, we are using the popular Barbie data set. So this Barbie data set basically contains conversations having intents like restaurant information, restaurant booking, restaurant phone, restaurant address, etc. And these are the popular intents in this particular data set named the Barbie. And we have basically extended this Barbie data set. Okay, so this Barbie dataset is having intense restaurant information where user is asking information about a particular restaurant, or the user wanted to book a particular restaurant, or user is interested in getting the phone number of a particular restaurant, or user is interested in interested in getting the address of a particular restaurant. And there are some common slots like location, cuisine, number of people, restaurant name, and the price. So this dataset is having 1 to 86 dialogues modified for the presence of multiple intents in a particular dialogue, annotated for its corresponding intent, slot, and sentiment labels, along with the visual communication of user's choice of a specific entity through images. So this dataset also contains a total of 1460 images of various slots and the types. So this is an example of a data set. You can see the user is saying good morning. Agent is saying hello. How can I help you with today? Okay. Here you can see that we are identifying the intent as well as the slots and the sentiment. So till now the sentiment is neutral. Now the user is saying I would like to book a table for 2 in London in a moderate price range restaurant. So here the intent is asking for the restaurant, the location, these are the slot values. The location is the London, number of people is equal to 2, and price is the moderate. And the sentiment is still neutral. So agent is saying, I am on it. So here the intent is information, sentiment is basically neutral, there is no slot. Now there is silence. So the intent is again the silence and sentiment is neutral. Now agent is asking any preference on a type of cuisine. Okay, so here the basically agent is requesting for food. So the intent is requesting for a food and the sentiment is neutral. Now the user is showing an image. Okay, so agent is saying, did you say Chinese cuisine? So yes, so here you can see the user is showing an image. So from the image, the agent is basically extracting the relevant slot information. So the corresponding intent is informed and the food is equal to Chinese. So this is the slot and this is automatically extracted from the image and the sentiment is still neutral. Now agent is asking, reconfirming, did you say Chinese cuisine? So here it is a re-ask and the food is Chinese and the sentiment is still neutral. So user is saying obviously. So here it is a confirmation that the food is Chinese, but now the sentiment becomes negative because the user is not happy that agent is re-asking, because already user has mentioned that he or she likes the Chinese food and now agent is asking the same question. So it is basically irritating the user. So the sentiment becomes negative. So there will be a penalty to the virtual agent. Now agent is asking what category of restaurant are you looking for? So it is a request and it is asking about the category. Now the sentiment is neutral. So again, the user is showing an image. And from this image, the agent has to extract the information that the user is saying about the 5-star. So now the intent is informed, category is equal to 5 and the sentiment is equal to neutral. Agent is saying, okay, let me look into some options for you. So here the intent is informed, sentiment is equal to neutral. There is a silence. So the intent is silence, sentiment is equal to neutral. So agent is saying AP call Spanish, AP user is giving some options. Agent is basically giving some options. AP call Spanish, London to moderate. So you know that AP call and the sentiment equal to neutral. So agent is again silence. So sentiment is still neutral. What do you think of this option? So user is agent is basically asking about the option. So you know that a user is saying no. Do you have something else? So here inform is equal to no and the sentiment equal to negative because user is not happy with this option. So user wants to get some more option. So agent is again searching in the database and then agent is showing some other option. So user is happy with this. User is saying that that looks great. So inform, it is an inform of type and then the sentiment is positive. So so agent is saying great, let me do the reservation. So it is basically reserving the restaurant. So sentiment is still positive. User is saying, do you have its phone number? So it is again asking for the phone number. The agent is searching and then agent is providing the phone number. And then user is saying you rock. So you can see that user is satisfied with the agent. So basically the user's sentiment is basically positive. So this is a sample chat transcript from the visual CentiVA dataset. So this is our proposed methodology. You can see that there is an intent classification module. So intent classification module is identifying the appropriate intent of the user's communication. Then there are some slot filling module. Slot filling module is extracting the useful information. Like here, the 2 people and 2 day are the slots. Then in case if the user is showing some image, then there is an image identification module. This image identification module is extracting some relevant objects from the images. And then there is a sentiment classification module, which is responsible for identifying the user sentiment. So all these basically constitute the state space, and this state space is basically given to this hierarchical RL model. So there is a top level intent meta policy and the lower level controller policy. So the top level intent meta policy is selecting a particular intent, and then accordingly the lower level controller policy is invoked, and then accordingly it will basically try to serve all the slots. It will try to identify all the slot values from the users utterances. So it's a hierarchical reinforcement learning. In the top level, we have to select the appropriate intent to be served. And then accordingly for a particular intent, we have the lower level controller policy. So lower level controller policy will basically converse with the user, and then it will extract all the relevant information or all the relevant slot values from the user. And then finally, accordingly, it will take an action, and this action will be translated into system response by the natural language generation module. So this is our overall diagram of the chatbot. And you can see that for the intent classification, we have used the CNN based model, CNN followed by the multi-layer perceptron. So we are first generating the embeddings from the user's utterances, and then we are passing through the CNN layers and the multi-layer perceptron layer to identify the correct appropriate intent. Then we also have the BioSTMs. So these BioSTMs are helping us to identify the slots. These BioSTMs are also helping us to identify the sentiments. And also there is an image identification module. So image is passed through the ResNet, and we are getting the image vectors. And then there is a multi-layer perceptor. Multi-layer perceptron is basically identifying the objects, or it is identifying the category of the image. So then this is the slots identified from the images. We are concatenating them together, and then we are generating the multimodal utterance semantic state space representation. And this representation is basically given to the dialog manager, and the dialog manager is basically predicting some actions, and those actions are translated into system response by the natural language generation module. So now here there are some, as I mentioned, we have two types of rewards. One is a task-based reward, which I already discussed earlier in a previous work. Now here we have also introduced the sentiment-based reward. So the task of the sentiment-based reward is to make the user satisfied. So if suppose the user's sentiment becomes negative, that means the user is not satisfied with the action picked by the agent. So that is the motivation. So here you can see that we are computing the SZ. So P is the probability value output from the pre-trained intent classification module. So the intent classification module is giving some probability of different classes. There are three classes: positive, positive, negative, and neutral. So according to it is giving the output the probability values. So the probability value is greater than 0.5, and if the tag equal to positive tag, then we are getting this PS. Otherwise, if the tag is negative and 1 minus PS is less than 0.5, then we are getting value 1 minus PS. Otherwise, it is 0.5. And similarly, the reward function is calculated. If the tag is positive, then the reward is W1 into SZ. If the tag is negative, then the reward is minus W1 into 1 minus SZ. Otherwise, for neutral, the tag is SZ. So this way, we are computing the sentiment-based rewards. And finally, the overall reward is a task-based reward plus the sentiment-based reward. So task-based reward, already we have calculated I have already shown. It basically measures how many slots are available, how many slots are filled. And then here in this way, we are computing the sentiment-based reward. So it is the combination of these two rewards. So you can see these are the learning curves. So over the iterations, how the rewards are changing. So we are comparing with the randoms, flat, only task-based, only sentiment-based, and a combination of task-based and the sentiment-based. So when you're using both say task plus sentiment together, you can see that there is an improvement. So there is more faster convergence or reward is improving. So basically, this learning curve proves the utility of using the sentiment-based reward. And also we have done some user satisfaction. So we have manually evaluated, it is a human evaluation. We have done some human evaluation and we have computed in how many times user is satisfied. So we have taken the 100 utterances, 100 dialogues, and then we have computed with the user satisfaction. And basically you can see if we are showing the multimodal setting, if you are allowing the user to express himself or herself by using the multimodal features, either text or images, then there is more satisfaction. In 87 cases out of 100 cases, user is satisfied. And this is the situation where we are using two rewards, TR plus SR together. And now you can see we are also comparing the average turns. So when we are using both rewards TR plus SR in a multimodal setting, the system is taking less number of turns. So here you can see some performance, like agent is saying, what do you think about this option? Resto London moderate Chinese 5 stars. So here initially the sentiment is neutral. Now user is saying, no, do you have something else? So now the user's sentiment becomes negative. So from here, the user agent can easily understand that the user is not happy with this particular option. So agent will show some alternative option. But if we are not using the sentiment-based reward, in that case, though here the user's sentiment becomes negative, but as there is no signal to the agent that the user's sentiment becomes negative, the user will not be able to show the alternative option. So user is still asking, no, do you have something else? So here, though the sentiment is negative, but the user is not, showing the alternative option. So basically, you can see by incorporation of the sentiment-based reward, the agent is capable of understanding the user's, sentiment or the user's intention correctly. So there is some image identification error as well. So you can see like, if, for example, if these are the images, so here it is a Chinese image, it is also Chinese, this is the seafood. But as the objects remain same, it's very difficult because, there is a overlap between these different categories. So the objects in the Chinese food, objects in the seafood are mostly similar. So by seeing these images, it's very difficult to identify the correct category. So the upper image gets misclassified as the lower. So although these images correspond to the Chinese food, but maybe the system, our image identification module is predicting them as the seafood. So this is these are some errors that are there in the system. And now I will just briefly discuss about how can we basically use the transfer learning concept. You know that as there are multiple domains, like for example, here we are working on the restaurant domain, but suppose you have to also work on the airlines domain. So if there is a change in the domain, then how can you utilize the same chatbot or the same conversational agent to converse with the agent in some other domain? So for that, we have to use the concept of transfer learning. So suppose the agent is already trained using the utterances of a particular domain, so maybe the restaurant domain. So how can you use this? How can you use this information of the semantic, so the understanding of the agent for solving for using this in some other domain? To develop a multi-domain, multi-intent based task-oriented dialogue system by successfully combining hierarchical deep reinforcement learning and the transfer learning paradigms. So why hierarchical reinforcement learning? To develop a multi-domain, multi-intent based task-oriented dialogue system by successfully combining hierarchical deep reinforcement learning and the transfer learning paradigms. So why hierarchical reinforcement learning? It gives virtual agent the capability to handle complex and composite tasks of the user pertaining to multiple domains. So the user can easily solve the task of multiple domains if we can somehow incorporate the transfer learning concept. The transfer learning is basically the notion is to exploit or take advantage of the resemblance between the source and the target domain. So for example, if there is a restaurant booking and the hotel booking, then many of the intents are common between the restaurant booking and the hotel booking. So if we already train some networks, the policy networks for the hostel or the restaurant booking, maybe we can utilize the same networks for the hotel booking as well. So previous works were focused on creating end-to-end virtual domains, virtual agents independently for different domains. But that's very much time consuming and the complex. So can we somehow, suppose a virtual agent is already trained in a particular domain, can we use the same virtual agent for with minimal effort in some other domain? Because some of the domains have some common or the overlapping attributes, like the location, time, number of people. These are some common attributes or the common slot values present in multiple domains. So this is the idea that basically here what we have done is that we are using the transfer learning in the dialogue management. So suppose there is a dialogue manager trained on the restaurant domain. How can we efficiently use this by using the transfer learning for some other domain, which is the hotel information? So here we have successfully combined a transfer learning concept with the hierarchical reinforcement learning to build multi-domain, multi-intent based dialogue system. And the transfer learning basically helps us in improving the convergence. So initially the networks are trained for the restaurant domain, but now the networks will be trained for the hostel domain with the minimal number of utterances. So this is our overall idea. You can see that we have a domain policy. So it's a there are more number of hierarchies now. So there is a domain policy. This domain policy is selecting the appropriate domain. It's a top level policy. So accordingly, when we are selecting a particular domain, in a particular domain, there are multiple intents. So accordingly, there is an intent policy. So we have a source domain, we have a target domain. So accordingly, we are selecting a particular intent policy, and then there are several subtasks. There are many controller policies, and the individual controller policies will be invoked. Okay, so this is the overall framework. So there at the top level, there is a domain policy, and then the domain policy is selecting some intent policies. And then for individual intents, so now we need to make a map. So the source domain is having a set of intents, target domain is having a set of intents. We need to map the one intent of the source domain to one intent of the target domain. So depending on the semantic space or depending on the semantic information, we need to map the intent of the source domain to the intent of the target domain. And then maybe this network can be shared their weights. So suppose we have trained the one intent policy for the source domain, and suppose intent 1 is very much similar to intent 2 of the target domain. Then maybe what we can do is that we can borrow the weights. We can not, instead of initializing this network by some random weights, we can utilize the pretend weights of this particular network to initialize the network of the intent 2. So this is basically the transfer learning concept. So without transfer learning, the two domains are trained independently, where the weights of the network of each domain are initialized randomly, which produces dialog states from unique or distinct distributions. Also, the output space of the set of actions are as well independent of the other domains. So we apply transfer learning from the source to the target domain only for the lower level controller policies. Because the virtual agent interacts or elicits information from the user with the help of only the lower level controller policy. Rest of the higher level meta policies help decompose the composite task into multiple subtasks in different granularities not known to the user. So basically, we are using the transfer learning concept. So as I mentioned that first, we need to map the intent to intent. So like depending on the semantic, we need to understand the semantic information of a particular intent, semantic representation of a particular intent, and then we need to map the intents of the source domain to the intents of the target domain. So here is the mapping. So we are mapping this, maybe this intent one is mapped to the intent one of the target domain. Intent two can be mapped to the intent end of the target domain. So, and now instead of each intent is having its own network or the own policy network. So now while training the sub-networks of the controller policy of the target domain, the weights of the neural networks are not initialized randomly. Rather, we are borrowing the weights from this source domain. Rather, the weights of a chosen subnetwork of the source domain for both input and the output space are copied to a subnetwork of the target domain. Then the subnetwork pertaining to the target side is further trained to optimize and learn behavior specific to the subtask. So this way we can basically improve the convergence. So here you can see we are utilizing the three domains: air travel, restaurant, and the hotel. And these three domains have some common intents like city, number of people. These are some common slots between the hotel and the air travel domain. So yes, so we have shown experimentally that if we are using the transfer learning, then the convergence is more faster. So you can see that intents restaurant transfer. So we are using the transfer learning, and if no transfer learning is used, so you can see by transfer learning is helping us in converging mass faster compared to without transfer learning. Yes, so I think, yes, I should stop now. Yeah, and also you can see that number of dialogues is also reduced. Like when we are using the transfer learning, we are taking, we are taking less number of turns for the convergence. Yes, so I think that is also in this particular, these are some of the publications. Yeah, you can maybe you can visit my web page and you can see this publication. So basically, yeah. So in this particular talk, I just tried to give you some understanding of the dialogue systems. So as I mentioned, this dialogue systems is a combination of many modules. So we have the dialogue act classification, we have the intent identification, slot filling, dialogue manager, and finally the natural language generation module. So there are many sub-modules, and the interactions of the sub-modules is very much interesting. So basically, I have discussed about some of the popular models which can be utilized for developing the sub-modules. So yes, so if you have any question, please feel free to ask. Students? So CSC IIT Gandhinagar, I think time was up to 12:30, no? This session was up to 12:30. Yeah. So any question from the student side, CSC IIT Gandhinagar?